Hi, in this video we are going to talk about stack in Java collections. In Java collections, stack is supported using two classes. One is ArrayDec class and the other is stack class. This is how these two classes are organized. So stack class extends the vector interface. So these are the two classes we are talking about, stack and ArrayList. ArrayDQ, and ArrayDQ class implements the deck interface. And deck interface is a child interface of queue interface, and these two both are children of collection interface. So collection interface is root, list interface has some extra functionalities, especially for list. Vector implements the list interface, and stack is a child of vector. So stack has all the functionalities of vector as well. And this ArrayDQ has all the functionalities of DQ interface, like inserting and removal both the ends. Both of these classes also have stack functionalities like push, pop, and peek. Now the question arises, which one of these two should be used? The answer is ArrayDec or ArrayDQ, especially in a single threaded environment. The stack class inherits from vector class, and vector is a class which is a thread safe class. Also, it is a legacy class. It was there before collections framework. This vector class has functionalities to ensure thread safety in the functions. And if you are working in a single threaded environment, then these thread safety functionalities, they are going to cause extra overhead. So in a single threaded environment, we should use ArrayDec only. Here is an example. We have created a stack using ArrayDec. However, you can create the stack using stack class also. So the point is, their functionalities, their return values, parameters have the same meaning, the functions that we're using, push, peek, and pop. So if you just replace this line with this line, this code will still work the same way. Let's now understand this code. We create an empty stack, then we push 10. So 10 goes to the stack, then 20 goes to the stack, then 30 goes to the stack. Then we do peek. So when you do peek on the stack, it gives you the top of the stack. So you get 30 as output when you print s.peek. Now when you do s.pop, it takes out the top of the stack from the stack and returns the top item that is removed. So 30 has been removed and 30 has been returned. So 30 is printed on the screen also. Now 30 is gone. So we do peek again. So now when we peek, we get 20. So please note that 20 is not removed. Peek function does not remove the top item. It simply gives you the top item. And pop function, it gives you the top item and also removes the top item. So we are calling peek again here. So we are going to get 20 this time, because 20 is the new top. 30 has been removed by this pop. So our output is 30, 30, 20 of this program. Here are two more functions that we generally use with stack. One is size, that tells you how many items are there in the stack. So we have added 3 items, our output is going to be 3. The other function is empty. This function tells you whether the stack is empty or not. So in this case, our stack is not empty, so we are going to get the output as false. Let's now talk about time complexities of all the operations. So push operation, pop operation, and is empty, size, peek, all these operations are constant time complexity. They have the time complexities big O of 1. And please note that both implementations in Java, vector and ArrayDQ or ArrayDec implementation, they both are array implementations. And in array, you can always maintain one end where you can remove and add items in big O of 1 time complexity. Right? As for simple implementation, you can just maintain the last element as the top element, right? And you can add at the end and you can remove from the end in big O of 1 time. Also, these are dynamic sized array implementations. So this big O of 1 for push and pop is amortized time complexity, not the worst case, because internally you are using a dynamic sized array. So there might be resizing while when you are inserting the elements or removing the elements. So resizing might be involved, and big O of 1 is amortized time complexity. To clarify it again, what is amortized time complexity? Amortized is if you are doing n operations and if you find out average time of these n operations, it will be big O of 1. However, one of these n operations can be costly, and that's what happens in dynamic size arrays. When you do resizing, one operation becomes one big O of n, then you have many operations which are big O of 1. So overall time complexity you get is big O of 1 only.